You have spent this whole series learning algorithms, a dozen of them. Here is the entire toolbox, on one screen. But the real skill is not memorizing them. It is knowing which one to reach for. And that comes down to a single question you ask every time. What does my data look like, and what am I asking of it? Answer that, and the right tool almost picks itself. Let us build the map. One honest note before the tour. Everything here is free, the whole map, no wall. This exact visual style is the idea behind my book, Algorithms and Data Structures, Visually Explained. 23 algorithms, each a clean diagram plus runnable Python. It is the perfect companion to this finale. $24, link in the description, totally optional. The full crash course is right here. Now, let us build the map. Start with the one lens behind every choice, Big O notation. Big O is not scary math. It is just how the cost of an algorithm grows as the input grows. And it gives us a ladder, from best to worst. O of 1, constant, instant, no matter the size. O of log n, it barely moves as data explodes. O of n, linear, cost tracks the input, 1 for 1. O of n log n, the speed of a good sort. O of n squared, nested loops, and it hurts fast. And O of 2 to the n, exponential, the danger zone. Every tool we pick is really a bet on where it lands on this ladder. Lower is better. Keep this yardstick in your head. First job, searching. You have a pile of data and you want to find something. The question is, what shape is the data in? If it is unsorted, you have no choice. You scan every element, one by one, linear search, O of n. But if the data is sorted, you can be far smarter. Binary search checks the middle, throws away half, and repeats. That is O of log n, a million items in about 20 steps. Need to look something up by an exact key, like a username or an ID. A hash table gives you that in O of 1 on average. And if you only need a yes or no membership check with almost no memory, definitely not, or probably yes, that is a Bloom filter. Which brings us to sorting, because sorting is what unlocks binary search in the first place. The simple sorts you write by hand, like bubble sort and insertion sort, compare neighbors again and again. They are O of n squared, fine for a few items, painful for many. The real sorts, merge sort and quicksort, split the data in half and conquer. They land at O of n log n, and that gap is enormous at scale. But here is the honest advice. You almost never write these yourself. Your language's built-in sort, like Python's timsort, is already O of n log n and battle-tested. Call it, then let binary search take over. Next, recursion, and its powerful cousin, dynamic programming. Recursion is simply a function that calls itself. It has two parts, a base case that stops it, and a recursive case that shrinks the problem. Elegant, but there is a trap. Compute Fibonacci the naive recursive way, and it recomputes the same values over and over. That is O of 2 to the n, exponential, and hopeless past 40. The fix is dynamic programming. When subproblems overlap, remember each answer the first time and reuse it. That single change collapses O of 2 to the n down to O of n. Dynamic programming is that whole idea in 3 words, remember and reuse. Now the data structures themselves, and picking one is a decision about how you will touch the data. An array is a numbered row. Reaching item 5 is instant, O of 1, but inserting in the middle means shifting everything down. A hash table gives O of 1 average lookup by key, but it is unordered, no sense of first or next. A binary search tree gives O of log n operations and keeps everything in order. So ranges, next, and previous all work. And a graph is for relationships, nodes and the connections between them, like friends, roads, or web links. Match the structure to your access pattern. Once your data is a graph, you need ways to walk it. Breadth-first search uses a queue, exploring layer by layer. It finds the shortest path when every step costs the same. Depth-first search uses a stack, plunging deep before backing up. Add weights, like roads of different lengths, and you want Dijkstra's algorithm, the math behind GPS routing. Give Dijkstra a heuristic, a sense of which way the goal is, and it becomes A star, aiming straight at the target. And when there is an opponent, Minimax plays adversarial games like chess. When the space is astronomically huge, a genetic algorithm evolves a good enough answer. So here is the payoff, the framework that ties it all together. You do not memorize algorithms. You ask a short chain of questions about your problem, and each answer points to a tool. Is your data sorted? Sorted means binary search, unsorted means a linear scan or a hash table. Do you need order, or just membership? Order means a search tree, membership alone means a hash set or a Bloom filter. One shortest path, or every connection. Unweighted means BFS, weighted means Dijkstra or A star. Do your subproblems overlap? Then it is dynamic programming. Is there an adversary? That is Minimax. Is the space too big to search exactly? Evolve it with a genetic algorithm. Read the shape of the problem, and the tool falls out. So there is the whole toolbox, on one screen. Big O is the yardstick, how cost grows. Linear search scans, binary search halves. Hash tables give O of 1 lookups, Bloom filters give cheap membership. Merge and quicksort sort in O of n log n. Recursion calls itself, dynamic programming remembers and reuses. Arrays, hash tables, trees, and graphs each fit a different access pattern. BFS and DFS walk graphs, Dijkstra and A star find weighted paths, Minimax and genetic algorithms handle adversaries and huge spaces. 12 tools, but you do not memorize them. You recognize which shape of problem you have, and the right one is already waiting. And that closes the series. We started with Big O, and ended with a whole map of when to use what. That is the skill that actually makes you dangerous as a programmer. If you want to go deeper, every topic here has a full written guide, all free. And if you want the whole thing in one place, 23 algorithms, each diagrammed with clean Python, my book is linked below. $24, and a natural next step. One last thing, pick a problem you are stuck on, and tell me in the comments which tool you would reach for. If any topic went by too fast, every one has its own video, go rewatch it. Thanks for watching the whole series. Now go choose the right tool.